Okay, in example 1, I say that suppose you have a polynomial with zeros x is equal to -2, so notice that that is a real zero, and x equals 3 plus I, which is an imaginary zero. Therefore, what do I know? That it must also have its conjugate pair as a zero as well, and so that conjugate pair would be 3 minus I. So this polynomial has at least 3 zeros. I've given you 2 of them, but really what I've done is I've given you 3 of them because the implication is that the conjugate pair is a 0 as well. So what is the minimum degree of this polynomial? Well, that would be 3 because we have at least 3 zeros, and by the fundamental theorem of algebra, the number of zeros has to equal the degree of the polynomial. So this is at minimum a 3rd degree polynomial. Now we want to write the polynomial in factored form. So if x equals -2 is a 0, what's the factor that goes along with that? It would be x plus 2. Now here in part B, we want to use linear factors. So for the imaginary zeros, this is going to look a little silly maybe at first, but I'm going to put x minus 3 plus I. That's going to be my first linear factor, and then x minus 3 minus I. Notice I've got those in parentheses so that it's actually correct. And so this would be my polynomial in factored form if I was asked to use linear factors. Okay, in letter C, I'm asking you to write the polynomial as a product of linear and irreducible quadratic factors with real coefficients. And so what I'm essentially asking you to do here is to rewrite this with x plus 2 down here, but then to multiply these 2 linear factors together so that you get an irreducible quadratic. Now, I don't know about you, but that does not look like a ton of fun to start multiplying out. And so the good news for us is that there is a shortcut to make this much easier. And so here's what this shortcut says. It's x squared minus the sum times x plus the product. And so what we're going to do is we're going to find the sum of our 2 zeros. And so remember our 2 zeros that were imaginary were 3 plus I and 3 minus I. And so when I add those together, what I'm going to get is 6 because the i's will cancel and 3 plus 3 will give me 6. And then I'm going to multiply them. And if you want to do this in the calculator, then by all means, you're welcome to do that. Just make sure that you put it in the calculator exactly the way I've written it down here with parentheses, otherwise you won't get the right answer. And what you're going to get here is 10. And so my irreducible quadratic factor is x squared minus the sum, which was 6x, plus the product. And so there is my polynomial written as a product of linear and irreducible quadratic factors with real coefficients. Now, in letter D, we want to write the polynomial in standard form. And so what that means is that we're going to take what we got in letter C and we're just going to multiply it all out by distributing so that we get it in standard form. And so what I'm going to do here first is I'm going to multiply the first thing in this little binomial by all of this right here. And so what that's going to end up giving me is x times x, which is x cubed, x times -6x right here, and that's going to be minus 6x squared, and then x times 10, which is going to be 10x. And then I'm going to take the second term in that binomial and multiply it by all of this trinomial. And so 2 times x squared is going to be 2x squared. I'm going to write that underneath the other x squared term to keep this vertical and lined up, because here in a minute when I add them together, now that I see them right on top of each other, I can just add vertically and it becomes much easier. 2 times -6x is going to be -12x, and I'm going to put that underneath the 10x that I already had. And then 2 times 10 is going to give me 20. And so when I am ready to add all of this up, I just draw a little addition bar here, and I have x cubed, -6 plus 2 is going to be minus 4x squared. 10x minus 12x is going to be negative 2x, and then plus 20, and that is my polynomial function in standard form with these two zeros, but again, with the implication that we've got our conjugate pair, that conjugate to 3 plus I, which would be 3 minus I. Okay, I really like this next example because I think it really ties together some of the things that we've been talking about and illustrates it to you in a nice way through example. And so previously we used synthetic division to show that a value of x was indeed a zero of a function by synthetically dividing and showing that the remainder equaled to 0. Now, if I told you that one of the solutions to the equation x squared minus 4x plus 5 was x equals 2 plus I, let's use synthetic division to show that that is really a 0. So this is going to be a new kind of synthetic division because it's going to be by an imaginary number. And I don't want you to freak out too much about that. It's going to be the exact same process. It's just that when we're adding and multiplying, it's going to involve imaginary numbers, not just real numbers. So I'm going to list my coefficients of my polynomial, 1x squared minus 4x plus 5, and draw a vertical bar. Drop the first number down. 1 times 2 plus I is just 2 plus I. When I add that to negative 4, what I'm going to get is negative 2 plus I. And then the next thing you're going to do is multiply 2 plus I times negative 2 plus I. And if you want to do that in the calculator, then by all means, please do, and make sure that you put both numbers in parentheses. I'm going to illustrate this for you in more detail later on in the notes, but for now, just take my word for it or see for yourself that when you plug this into the calculator or multiply it out by hand, that you are going to get negative 5, and so that gives you the remainder that you want of 0. And so because this started with x squared, when we synthetically divided, we got down to x, and so this says x minus 2 plus I, and to find the remaining 0, I am going to set that equal to 0 and solve, and so that means I need to add 2 to both sides and subtract I from both sides. And so my other 0 to this quadratic is 2 minus I, which I would love for you to notice, hopefully you already did, that that's the conjugate of the given 0. So synthetic division showed that that given 0 indeed was a 0, and then it beautifully showed that the other 0 was the conjugate pair to the given 0, 2 minus I. Okay, so just a couple of more words on example 2. In that last example, those two conjugates were both solutions. That is not a coincidence. In a polynomial, if you have an imaginary 0, you also have to have another one, and it has to be the conjugate of your given one. So just keep an eye out for that. That's going to be very important as we go on down the road here. So in example 3, we're going to do something similar to what we did in example 1. We're going to write a polynomial function of minimum degree in standard form, which means it's going to be all multiplied out by the time we're done, whose given zeros and their multiplicities include those listed below. So we have x equals negative 5 and x equals 4i, but those are not the only zeros for this polynomial, because remember, if I have an imaginary 0, 4i, I've also got to have its conjugate, negative 4i. So be careful and stay on the lookout for that. Okay, so for this real 0, x equals negative 5, that means I'm going to have the linear factor x plus 5. And what I'm going to do for these imaginary zeros is I'm going to use my shortcut that I introduced to you a little bit earlier to write my irreducible quadratic. And so the first thing we need to find is the sum of 4 plus I and 4i and negative 4i, and that ends up giving me 0. And then the product of those two numbers, which is going to end up giving me positive 16. And so my irreducible quadratic is going to be x squared minus the sum x. Well, the sum is 0, so I don't really need to put minus 0x and then plus 16. The last thing we want to do is just multiply all of this out. So this is just pretty easy distribution here. X times x squared will be x cubed. X times 16 is going to be 16x. I'm going to leave a little bit of space here so that it actually ends up in standard form, which means it's in the correct order. Here I'm going to have 5 times x squared, which is going to be plus 5x squared. That goes in the right spot there. And then plus 5 times 16, which is 80. And so my polynomial in standard form with the zeros listed would be the following. Okay, letter B is going to be slightly more challenging, but that's okay. It's not any different. It's just a few extra steps and a little bit more arithmetic and mathematics and algebra. So here we go. X equals -2. Notice here that it's got a multiplicity of 2, and so that means I'm going to have x plus 2, but it's going to be to the second power. Or really another way to say that is that I have x equals -2 occurring twice. And so here's the good news, is that I can use my shortcut not just on imaginary zeros, but also on real zeros like -2 and -2. And hear me real carefully. You don't ever want to mix real and imaginary and use them together in the shortcut. You want to use the shortcut either for only imaginary or only real. So don't mix them. Don't do one real and one imaginary. That's not going to go real well. But if you have 2 real zeros, you can use the shortcut to write the quadratic. And if you have 2 imaginary zeros, you can use the shortcut to write the quadratic. So I'm going to do that here for -2 and -2. So if I add together -2 plus -2, that's going to give me -4. And if I multiply -2 times -2, that's going to give me +4. And so that means the quadratic for those 2 zeros is going to be x squared minus the sum x, which is going to end up being plus 4x, and then plus the product, which is 4. Okay, so that takes care of the quadratic for my real zeros, but I've also got a quadratic for my imaginary zeros, and remember that they come in conjugate pairs. And so again, I want to find the sum of these. You're more than welcome to utilize your calculator in order to do this if you need to. What you should end up getting for the sum is 4, and then when you do the product, 2 plus 3i times 2 minus 3i, what you should end up with is 13. And so the irreducible quadratic for this these 2 imaginary zeros is going to be x squared minus the sum of x plus the product. And so now, to get this into standard form, I'm just going to have to do a lot of distributing. And so I'm going to break this up just a little bit by doing the following. I'm going to say x squared times all of that parentheses. And so x squared times x squared minus 4x plus 13. And then positive 4x times all of that, so plus 4x times x squared minus 4x plus 13. And then finally, plus 4 times that second trinomial. And this is just going to help me do it a little bit easier. If you have a way that you like better, then by all means, you're more than welcome to do that. And so here we go. I'm going to start multiplying out. So x squared times x squared is going to give me x to the 4th. X squared times negative 4x will be minus 4x cubed. And x squared times 13 will be positive 13x squared. Okay, I'm ready to go on to the middle term now. 4x times x squared is going to be 4x cubed. I'm going to put that underneath the other x cubed term that I already have, just to keep things lined up and organized. 4x times negative 4x is going to be negative 16x squared. And again, I'm going to write that vertically just to make things a little bit easier on me. And then 4x times 13 is going to end up being plus 52x. Okay, I'm ready to move on to the last bit of distribution here. So 4 times x squared is going to be plus 4x squared. 4 times negative 4x is going to be minus 16x. And 4 times 13 is going to be plus 52. And then I am ready to add all of that together. And so I'm going to get x to the fourth. I'm going to have no x cubed since those cancel out. 13 minus 16 is negative 3, plus 4 is 1, and so this is going to be plus 1x squared. 52x minus 16x is positive 36x, and then finally plus 52. And I always like doing that little addition bar because then you can just make it the top part of the box for your answer. And so if you have any questions about that and how I like to organize the work there, please feel free to reach out to me and I would be happy to explain anything that's not making sense.